class we will be discussing on the polishing operation known as crystallization, which is one of the important operation for getting highest purity of fine chemicals and protein and other pharmaceutical products for biotechnological applications. So first of all, we need to know why we are doing for crystallization. That is actually it is the formation of solid particle of defined shape and size within a homogeneous phase. So actually we are going to recover those things which are predictable in manner. So essentially you can see the crystal shape and size. Most of the time they will be regular shape, they will be uniform size, and it actually helps for having acceptance of the products to the public more acceptable rather. Crystals will be exceptional purity also, so high grade of purity is possible when you are doing crystallization process. Formation of crystal makes operation easier because if you are having crystal formation we can actually take it out very easily, maybe from filtration or all those other processing steps can be taken care, and we can recover it more easily compared to any other process. It improves the appearance and acceptance as most fine chemicals and pharmaceuticals are marketed in terms of crystal form. Now we need to know what are the basic concepts involved in crystallization process. Basically all the crystallization process depends on important property of a solution, that is actually the supersaturation, how much the content or the compound is dissolved in the solution, what is the concentration you need to know. So essentially crystallization to occur, the first and foremost thing is the solution must be supersaturated. Supersaturated means the amount of solute dissolved should be more than its solubility. So if it is going beyond its solubility and still in solution, that is called supersaturation. So we should have more and exceeds its saturation concentration absolute, that we already discussed. And there can be some other scenario apart from supersaturation also. There can be, if it is supersaturation, the solute presence is depending on how much amount of solute present, what is the behavior, the property of the solution can be of metastable form, because if you are having some solute excess of saturation and it can deposit on existing crystal but no new nuclei are formed, so that means crystal growth is permitted. That kind of beyond saturation level, that concentration range is called metastable range. We can have intermediate where growth of existing and formation of new nuclei can happen. So here actually nucleus formation and crystal growth both can happen together. And when we can have actually nuclei formation from clear solution, that is the labile zone. So depending on the scenario, what is the extent of supersaturation, three different phases can be observed. So basically if you see, the labile zone concentration is likely to be more, and when you are having intermediate zone concentration you can have some growth and formation together, and metastable zone only growth is possible but no new nuclei is formed. So this three scenario is really understood. Now supersaturation, as we are referring every time, we need to know actually how can we get it, how can we attain it. So it can be achieved by three different way. Maybe first of all the most widely used is reduction of the temperature, though here we are not showing the solubility of a compound is a function of temperature. Increasing temperature generally increases the solubility, so decreasing some temperature will actually reduce the solubility, but if the solute dissolved is more, that means it is going to attain supersaturation. Evaporation of solvent, if you reduce the volume of solvent, so your solution will become supersaturated because the existing amount of solute remain unchanged. And solvent addition, sometimes we add some solvent which can actually change the solubility of your original liquid or maybe the liquid phase. So that is some additional, you can say some additional solvent we are adding, and which is going to change the behavior and increasing the supersaturation of the solution. Now we have some other terminologies like fractional and molar supersaturation. It is a little bit same way we discuss it. So supersaturation means how much beyond the its saturated concentration. So if I'm talking about in a mole fraction terms, then you will say fractional supersaturation, because mole fraction of solute what is present currently in a solution, and mole fraction of solute when it is in saturation or its solubility limit. So the difference is going to give us in case of fractional supersaturation, because both of them are fraction. Or molar supersaturation, if we are going to calculate in terms of concentration terms, molar concentration, mole per liter, so that gives you the molar supersaturation of the solution. Now what are the steps involved in crystallization process? Basically, when you are going to discuss about crystallization, the first thing is formation of nuclei, and then growth steps will be required. So nucleation, that is birth of new crystals, and crystal growth of the existing crystal. It may happen in simultaneous process. So growth and crystal growth, existing crystal may grow further, new crystal may generate. These things can go together. Ratio of rate of nucleation to growth control the size distribution of the product obtained. So it is very important aspect at what rate the nucleation is happening, at what rate the growth is happening. It will tell the size distribution, because at any moment how many nucleus are there, and how many different crystal has grown to what extent. So all those things is going to give you a complete distribution of crystal size. General factor that affects the nucleation and growth kinetics, that you already know. It can be some physical parameter as well. So supersaturation is the first one, the solvent, temperature, a presence of any other impurities which can actually help for production of crystals, or maybe nucleation it can assist. Solution viscosity, surface tension. Of course, we have not discussed is the degree of agitation, the surface of the container. All those things are also taking into picture. Now nucleation can be of different type. One is homogeneous nucleation due to supersaturation only, so we are not adding any other additives over there. Heterogeneous nucleation can be presence of some insoluble material on which the small crystals can further grow, or maybe some nucleation can be, you can say, assisted because of the addition of some other insoluble material. It can be dust, some small seed crystals. And secondary nucleation can happen because of the process involved in the nucleations. Here we can have some fluid shear nucleation because of the fluid flow itself. The shear force can result in generation of some nucleus which can further grow. Contact nucleation on, maybe depending on the contact surfaces which are present in your container or maybe crystallizer. So all the processes are actually not known how the nucleation happens, why some sorts of solid starts evolving out and growing. But empirically it has been modeled. Essentially, author have assumed that it is already dependent on the degree of supersaturation will be the guiding one. So dN dt, the rate of nucleation, N is nucleation rate, K is the nucleation rate constant, C and sister you already know, current concentration of solute in the solution, and sister is the saturation concentration. I is a constant rather, which depends on the solute, what crystals we are going to do. So all those parameters are involved here. So these are all empirical parameters, of course constant for a given sets of conditions. Now second aspect we need to know is about crystal growth. Crystal growth is also one of the important process which can be to some extent empirically modeled, of course. And here the uh, crystal growth rate can again be given by the rate constant K. The surface area of the crystals is very important, of course. More exposed surface area will add up more crystals for growing. And C minus C star, that is the saturation. So maybe the supersaturation level, molar supersaturation, we can simply say here. C is the concentration, C star is the saturation concentration. So M is the mass, K is the mass transfer coefficient, often written in two terms because it is not only mass transfer, it is actually involved of the reaction on the interface. So there is two process involved. One is the mass transfer process of the molecule which is going over the crystal surface, so there is a concentration gradient working on that. And second thing is the reactions on the surface of the growing crystals. So combinedly we can write 1 by k is the inherently mass transfer and the reaction rate constants together. So if we assume a crystals can be some cubic size, then if we say size is S, then we know mass will be the density rho, and SQ is the volume, because if S is the size, all the size, it is a cubic, so SQ. And area will be 6S square because 6 different faces are there for a crystals, and each side is S, so we can have 6S square. And if S equal to L, the length of the crystal, if we assume, then we can have more simplified arguments will come for any other shape. So same way we can say the mass for any other shapes will be rho some function 5e L cube. So it all depends on the shape factor, what kind of crystals. So 5e is actually other parameters. For example, if it is a spherical, so we know 4 by 3 pi. So 4 by 3 pi R cube is the volume. So 4 by 3 pi is actually pi v. Similarly, for surface area, for sphere we know 4 pi r square. So 4 pi, this is a constant, of course. So this is the constant. Phi a is the area term, area parameter, which is depending on the shape and size. L square is the length of the crystal. So L square for surface area, L cube for mass. So if we know mass and surface area, we can put it together over here. So conversion of mass dm dt, we can write rho 5v L cube, the derivative. And here similarly, as you have written ka, so instead of k a, we can simply write k equal 1 by k equal to 1 by k plus 1 by the rate constants for mass reaction rate constant. So 6 phi a L square, and the combined k terminal over here, so 1 by k plus 1 by k tau. C minus C star is the concentration difference between these two phases. I mean to say saturation and current concentration. It can be really simplified further. So simply you're making the derivative in terms of L, we can write dl dt. This thing is really no change, and all the constant terms if you put together, we will say dl dt equal to this block 2 phi a by rho 5 e 1 by k 1 by kappa. These things, all blocks, is actually constant, so we are writing as kg c minus system. So essentially what happens, the crystal growth rate length time is going to be proportional with the degree of supersaturation. That's all. We'll be discussing other things in our next class.